characteristics, ideal IV characteristics of MOSFETs, and in actual MOSFETs, there are a few nonlinear effects that one needs to consider. So we have not talked of any finite output resistance. That's the first one in the saturation region. So if you recall, MOSFETs in saturation region, they they have a drain to source current, which is for a given gate source voltage is constant. Okay, it is not depending on any increase in VDS, any large increase in VDS rather. Do you see that the output resistance is given by the gradient in this region, which is equal to well, the gradient of this curve is, you can see, is delta ID, okay, divided by uh, delta VDS, okay. Well, that's the gradient of the curve, but for the resistance, you need to take the inverse of this quantity. So, and delta is a very small quantity over here in the limit. So this is your output resistance. Okay, so this is basically zero. Okay, so delta VDS, even it's large, you don't have any change in the current. Okay, so the output resistance was zero, but this is not the case. Okay, this is the well, you don't have a zero output resistance. Output resistance turns out to be finite. Okay, the non-ideal characteristics, they don't produce a flat shape or a plateau shape in this saturation regions. So it works out something like this in a practical MOSFET. So you for a given VGS, well, you have a non-zero output resistance, and due to this non-zero output resistance, your curves are a little bit they're rising with increasing VDS. You have some increase in the current ID. Okay, so this is what happens in actual MOSFETs, or let's say MOSFETs having a finite or a small channel length. Okay, so this is the story of actual MOSFETs, and these are non-idealities, non-linear or non-ideal things that we consider in the IV characteristics. So one is that you have a finite output resistance, and then there is a body effect. Okay, which we are going to discuss later on. Uh, the body effect is that if you are having more than one PMOS NMOS device on a single substrate, then um, owing to the non-uniform length of the channel, you have a variation in the threshold voltage. Okay, so that might degrade the performance of the device, and then you have this sub-threshold conduction effects, breakdown effects, temperature effects, which we are going to discuss in detail one by one. So let's start with the first one, finite output resistance. The thing is that, okay, as I've explained, that when a MOSFET is biased in the saturation region, the drain current is independent of the drain to source voltage. Okay, this is what we've seen earlier. Okay, in our uh, in the MOSFET series lectures. So increasing drain source voltage beyond VDS saturation at each given curve for VGS, for the family of the curves corresponding to VGS, well, there is no increase in ID. ID stays there; it's constant. Okay, and the slope of this curve is zero. The slope of this curve uh, is zero. So uh, you're not considering any output resistance over here. But practically, in actual MOSFET, ID versus VDS characteristics have a non-zero slope that does exist beyond the saturation point. So for VDS greater than VDS set, the actual point in the channel at which the inversion charge goes to zero, it moves away from the drain terminal. So if you recall, what we have seen before was that the situation was like this. If you consider a 2D um, uh, a two-dimensional cross-sectional view of the MOSFET, you have the gate metal over here. Okay, so let's call this the gate metal. This could be aluminum or a polycrystalline heavily doped silicon material. Okay, so this is your metal. This is your gate metal, and then you are having an oxide, which could be silicon dioxide, any oxide insulator. Okay, which is going to uh, offer insulation between the gate and the substrate body, and then you have those um drain and source regions, okay, which are connected by to a substrate. If it is an NMOS, then you have this N doping over here. Okay, so this is like this, like this. So this is your, let's call this drain terminal. Then you have another source terminal. So basically, source terminal and your bulk, the body terminal or the bulk terminal, the substrate is they're short circuited. Okay, so okay, it's like this. So this is kept at ground, and this is connected to the bulk terminal. So let's say this for an NMOS, we have this p-type substrate over here, and we apply a negative, a positive gate voltage over here. So VGS is positive; it's greater than 0. So VGS is greater than 0, such that positive charges are going to develop over here. Okay, since the negative of the battery is over here, we have this body at negative. The electric field direction is like this in the oxide. Okay, and due to this, you are going to enhance the channel. You're going to produce an inversion layer like this. Okay, if this VGS is greater than VDN. Okay, let's say this is greater than 0. Well, let's say this is greater than VDN. Okay, so the channel is established. We have an inversion layer over here. Okay, which is consisting of negatively charged particles, which are minority carriers of p-type. Now, so the holes are at the bottom. Okay, they are since the bulk is connected to a negative potential in the circuit, so the holes which are the majority carriers in p-type, they appear on the most of them are accumulating at the bottom of the substrate. So what happens is that as you go on increasing VDS, okay, VDS is again positive, and due to this positive terminal of the VDS battery attached to this drain terminal, you are going to introduce some depletion region, okay, because this is p-type material, and over here you have N doped drain terminal, okay, which is already reverse biased due to the p-n junction. Since this VD is so positive terminal is over here, you're going to reverse bias this, so depletion region is going to increase. Okay, and then you know that what happens is that you are going to pinch off this channel. Okay, the channel is pinched off and it tapers like this, and the channel width is compromised. Okay, so if you are going to increase the VDS even further, well, it's not going to it is going to reverse bias this this p-n junction substrate and the drain terminal, but it's not going to increase the drain source current. Okay, so that's saturation. What happens in actual MOSFET is that for VDS greater than VDS sat, the actual point in the channel at which the inversion charge goes to 0, it moves away from the drain terminal. So what it says over here is that you're not going to have something like this. So I mean, this point where the pinch off is occurring is at the drain terminal. This is at your drain terminal. So this point moves away from the drain. As a result, it could have moved somewhere near the at the bottom of the gate, or anywhere near the source terminal, even near to the source terminal. So what it results is that the channel length, this is the new channel length, let's call this L prime, and your original channel length was this much. Okay, taken from the drain where the pinch off would have originally occurred in ideal MOSFET towards the source. This is your original length. Okay, and you can see this L is greater than L prime. So your channel length has been compromised because the zero of the that point at which the inversion layer or the charge density goes to 0 is not at the drain terminal. It's not at the drain terminal. It's somewhere in between drain and source. It has moved in the actual MOSFET, and it has reduced the actual length of the channel of the inversion layer, and well, so the effective channel length decreases as a result, and this phenomena is called channel length modulation. Now, what is the effect of this channel length modulation? You see, ideally, this is the characteristic, IV characteristic for a given threshold voltage for the given gate voltage. This is the conduction parameter. This is the quadratic uh, current characteristics. So current has a quadratic characteristic with the VGS voltage. This is your ideal MOSFET. Practically, you need to include your VDS, the effect of VDS, which is going to produce a horizontal electric field, okay, because VDS over here is producing electric field. So this is positive, okay, and this is negative. So the horizontal electric field is like this, okay, which is going to be there in the channel, and it's responsible for the mobility of negative charge particles, and that's the perpendicular electric field due to the gate. So this horizontal electric field is responsible for moving the charges along the channel. So due to this, this is due to VDS, okay, and we are now considering the effect of VDS on the channel length modulation, okay. This lambda is a positive quantity, and it's called the channel length modulation parameter, okay. So in actual MOSFETs, the actual channel length is modulated, okay. It's not the original channel length. Original channel length is capital L, is from the drain to source, okay, which is greater than what we have in actual MOSFETs, that's L prime. So this is actual case of IV characteristics, and this is not exactly quadratic, okay. It depends on this depends on the channel length modulation parameter lambda, and it depends on the field that is being created by VDS, okay. So there's an exaggerated view of this current voltage characteristic shown in figure 20. Now you see over here, we don't have this ideal characteristics that we have seen before. These were the ideal characteristics for the given VGS from the given saturation point. We had the straight lines, okay, but now the slope 1 over R naught is finite. We have to consider this slope, okay. So if you're going to exaggerate these curves down to a point where they intersect, and this intersection is common with respect to all VGS curves. This is a family of VGS curves. VGS, if it is an NMOS, VGS is a positive quantity, and it is increasing in this direction, okay, because we are increasing the space charge density in the channel. I mean, the channel width is increasing, you're increasing the charges, so you're increasing the ID as well with VGS. But if you're going to exaggerate those curves, all the curves down to a point where ID is 0, so on this axis your ID is 0, okay, horizontal axis ID is 0. This intersects on the voltage axis, this is your voltage axis, and this is a parameter VA, which is written to the channel length modulation parameter. This is in volts, okay. uh, so well, when does this ID becomes equal to 0 is when in actual MOSFETs, it's because VGS is a non-zero quantity, okay. VGS is a constant, okay, in these curves. VDN is due to the fabrication of the device, and it's the minimum voltage required to turn on the device. It's non-zero. Conduction parameter is non-zero. So when does this ID become 0? Okay, the question is, when does this ID become 0, and what does the relationship does it has with the parameter lambda and VA? Okay, VA is the point where all these curves are going to intersect, and this on the voltage axis is called 1 over lambda or VA. So how does it comes is that if you consider ID equal to 0, well, VGS is non-zero, VTN is non-zero, TN is non-zero, then this implies the factor in the actual MOSFETs 1 plus lambda VDS. This factor, the second multiplying factor in the equation, should be equal to 0. In order to, this will imply that well, ID equal to 0 implies that this factor becomes equal to 0. Okay, and this further implies that your VDS is equal to minus 1 over lambda, okay, and we call this equal to minus VA. So this is so you see this V subscript capital A, we are calling this as 1 over lambda, okay, so reciprocal of the length modulation parameter, and that's actually the point on the VDS curve, okay, where all these curves, if exaggerated, they converge on the voltage axis, and they're given by the reciprocal of the channel length modulation parameter. So the curves, then they're extrapolated, so they intercept the voltage axis at VDS equal to minus VA. That's the point. That's a hypothetical point where all the curves are intersecting the voltage axis. So the voltage VA is usually defined as a positive quantity. The slope of the curve in the saturation region can be described by expressing ID versus VDS characteristic form in the following n-channel device. Okay, so it's no more a quadratic. It also depends on the second factor, 1 plus lambda VDS, where lambda is the channel length modulation parameter. Okay, so the parameters lambda and VA are related. Okay, so you see the thing is your current now is depending on this parameter lambda. Okay, because the length is not the ideal length we are considering from drain to source. It's less than the actual MOSFET. The point has moved away from the drain terminal. Okay, and due to that, the channel length has been modulated. Okay, the channel length is something else. So this current is basically depending on this parameter. So this is the actual relationship. This whole relationship constitutes your current, and that has to do with the electric field as well, which is being produced by VDS. Okay, that is constraining the length of the channel, modulating the channel length. VDS is what is modulating the channel length. So when 1 plus lambda VDS is 0 at extrapolated point, where ID equal to 0, at this point VDS is minus VA, which means that VA is 1 over lambda. So the output resistance due to channel length modulation is defined as R naught, which is the gradient ID over VDS. You take the inverse, that's your resistance. Because ID, in ideal case, there was no change. Okay, in ID, even for a large change in VDS. Okay, so you were not considering the output resistance for a given VGS, but here the situation is different. So if you take you have to consider the actual ID characteristics for actual drain source current characteristic for a transistor. This is for the actual MOSFET, not for an ideal MOSFET. Okay. So if your transistor is biased in the saturation region, well, the current is being defined for the given VGS and for the given threshold voltage conduction parameter in terms of whatever is the length and VDS. So that's the definition of the current. So the following equation uh, can be used to derive the output resistance, basically evaluated at the Q point when the transistor is being biased in the saturation region. Okay, so we are in the saturation region right now. Okay, so this R naught is the change in ID over change in VDS inverse, so it becomes in ohms. Okay, this quantity has to come in ohms because this is inverse over here. So a change in voltage over current V over A is amperes, so volts over it's ohms. So okay, you take the derivative, you're left with respect to VDS. So this becomes lambda Kn VDS Q VDN square, and this is what you have in the quadratic nature. You should look at the quadratic nature of the current over here, and this was what we had in the ideal case as well. So let's call this current as IDQ, and the Q point, let's say, is in the saturation region. Okay, so it just means this is the drain to source current. Okay, and this current is due to the biasing of the transistor. The transistor is in the saturation region. Okay, okay. So this quantity can be expressed as lambda IDQ over here. You take the inverse, you can express this as 1 over lambda IDQ as a reciprocal. And 1 over lambda is nothing but VA. Okay, so this quantity comes out in ohms. And you have to consider this parameter R naught. Okay, this 1 over lambda, if you recall, was 1 over lambda was VA. Now, if you consider, so VA has been substituted for 1 over lambda over here. Okay, we are 1 over lambda is going to VA. So this quantity needs to be considered in the small signal model of the MOSFETs if you are going to consider actual MOSFETs. This quantity has to be considered. This represents the finite output resistance R naught in the small signal equivalent circuit model, but it's not there in the ideal IV characteristics. Okay, in the ideal IV characteristics, your ID is not changing with respect to VDS. Okay, so that means you don't need to consider your you don't need to consider the output resistance. Okay, so but in actual MOSFETs, just remember that you have a finite slope, and this slope is 1 over R naught in 1 over ohms. So so you need to consider that in the equivalent circuit models of MOSFETs when you consider the small signal AC analysis. So that's your finite output resistance in actual MOSFETs. Okay.